Okay, good morning students. The last class we discussed about electronegativity and we discussed about factors affecting the electronegativity and we discussed about variations of electronegativity based on the groups and periods. Now we are going to study about a very important topic, that is electronegativity scale. It means the scales which gives the value of the atom having how much the electronegativity. The first one in that is a Pauling scale. Pauling scale. Pauling scale is based on the bond order. Pauling scale is based on bond energy, nothing but the energy required to break a bond energy is nothing but the energy required to break a bond energy is nothing but, he given one formula. The formula is X means electronegativity of A, electronegativity of B element, it's 0.208 root of del. Del is nothing but where root del is equal to electron of A atom and B atom. Okay, bond energy is nothing but energy of bond energy of atom A and B minus root of energy of A atom into energy of B atom. Okay, given the formula. Okay, next we are going to talk about another scale, Mulliken scale. The Mulliken scale gives the average of ionization energy and electron affinity. You see, Mulliken scale gives to measure the Mulliken scale you use average of ionization energy and electron affinity. We will write that Mulliken scale to find electronegativity equals average of ionization energy plus electron affinity, okay, by 2. This is a formula used to find the electronegativity by using Mulliken scale. While if you tell that electronegativity using Pauling scale, the formula is, this is a formula. Okay, next the third scale we are going to study, that is Fred-Ronchow scale. He given the formula for electronegativity to find equals Z effect square by R. ZEF means effect of nuclear charge. You see, effective nuclear charge. Then E square is nothing but charge on electron. R is nothing but covalent radius. These are the three scales used to measure the electronegativity. Next we are going to study about period of valency. Okay, next we're going to study about periodicity of valency, or maybe also called as periodicity of oxidation state valency. Okay, we have the we'll define that, or definition. The periodicity valency or periodicity of oxidation state valency is nothing but combining capacity of an electron. First definition is combining capacity of an element. Combining, or you may be write another definition or second definitions. Electron lose or gain, electron lose or electron gain or electron shared. Okay, for example, you take methane. Methane is nothing but CH4. Example, methane 4. You see here it is methane. It having the 4 valencies. The 4 valencies, you see 1, 2, 3, 4. Here the carbon is giving, means a carbon have bond between the hydrogens, combining with carbon and hydrogens, combining capacity of an element, that is carbon and hydrogens. Okay, valency, there is the 2 types valencies. Okay, valencies are 2 types. That is, one type is alright, valence is 2 type. One is electrovalency, one is covalency. Okay, what is electrovalency is nothing but number of electron lose or gain. You see, what is electrovalency? Electro means electrons. Electron valency means is losing or gaining. Okay, I'll write that number of electrons lose or gain. Okay, for example, you take NaCl. Here the metal means the electron, metal is giving to non-metal the electrons, means sodium giving the electrons to the chlorine, then sodium becomes cation, leaving the electrons, then chlorine is attracting the electrons, it becomes negative. Here 1 electrons are valency, means moving from sodium to chlorine, then we call it as 1 electrovalency. When come to covalence, number of bonds found by an atom. You see, number of bonds formed by an atom. For example, we'll take that bonds. Okay, we'll take that water, H2O. You see, if you talk here, the oxygen is bonded by an atom of hydrogen. Here bonding between the two hydrogens, while this is the first and this is second, then we will tell that it is 2 covalence. We will talk that it is 2 covalency. We understand the oxygen is bonded with the 2 hydrogen atoms. For that it will be 2 covalency. Okay. Next we are going to talk about for S block. S block, it having the 2, quite commonly we know that group 1, group 2. group 1 it's a ns2 configuration, sorry, group 2 ns2, group 1 ns1. It is alkyl metals, it is alkaline earth metals. You see, while taking the example for the alkyl metals, we take that the lithium, for example, its electronic configuration 1s2 2s1. The valency, you see, this is the valency where occurring, the s orbital must be filled with 2 electrons, but we are having the 1 valency occurring here, 1 valency. When come to alkaline earth metals, we take beryllium. If we write for 1s2 2s2, here 2 valency, the last orbital, how much electrons are present, that much of valency. Okay, for example, for if you take for p block elements like halogens, the halogens having general electron configuration ns2 np5, it's the last orbital, it is a 7 valency. For example, if we take the fluorine atomic number is 9, 1s2 2s2 2p5, it is second orbital, it's having 7 valency. Next we are going to discuss about d block elements. D block elements. You see, D block electrons are present in penultimate shell and outermost shell, correct? No, the electrons are present, sorry, we'll write electrons present in penultimate shell and outermost shell. Okay, you see, I will write the general electronic configuration for D block elements, that is n-1 d1 to 14 ns2. You see, here I told that the electrons are present in penultimate and outermost. You see, ns2, it is outermost shell. Then what about the n-d1 to 14 is penultimate shell. For example, we take the scandium, its general atomic number is 21, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d1 4s2. You see, the last valency means, actually if you write in the electronic configuration, first 4s2 3d1, correct? No, 3d1. Here the 4 and 3 orbitals, the number of electrons are 2 plus 1, it is 3 valency. Okay, you see what I told, that 3d and 4s, if we can write that 3d1 and 4s2. See what I told, n-1, n is nothing but highest number is 4, correct? No, 4 minus 1, okay, d, okay, d 4 minus 1 3, correct? No, it will be 3d. Then ns2 is nothing but n is highest number, no, is 4s2, correct? No, I am writing here, the 3d already we told that 1, then n is 4s2, correct? No, this is the, here the 4s2 is the outermost shell and 3d is the penultimate shell. Next we are going to talk about F block. Means we are finding only the valencies of the S, P, D, F. We are taking some examples. Okay, in F block electrons are present in penultimate shell, and outermost shell. We will write the general electronic configuration, that is n minus 2 f 1 to 14 n minus 1 d 0 to 1 ns2. You see ns2, it is outermost shell. What about n minus 1 d to the power of 0 1, it is penultimate shell. Then n minus 2, it is anti-penultimate shell of the f block elements. Now we are going to discuss about variations of valency in periodical table. Okay. Variations of valency in periodical table. Table is nothing but we will discuss about groups and periods, correct? No, it is groups, it is period. You see, first we are going to talk about valency. Valency in period, it goes on increases and then decreases. You see, in period valency goes on increases and decreases. You see, goes on increases first and then decreases. So we are not understanding, I will explain it. Example, we take the second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. You see, while valencies are occurring here 1 2 3 4 3, see again it decreases 3 2 1 0. You see, for lithium already explained, that is 1s2 2s1. The 1 is valencies are occurring. Beryllium all told that is 2 valencies, that is 1s2 2s2, correct? No, you are understanding? Similarly I am telling that here, if you boron, if you write 1s2 2s2 2p3, correct? No, like if goes on going, the what happening that the period in second period, not only period, in period what happen is to starting from it increases and then it will be decreases. Can you understanding in period? Now we are going to valency in periods. Valency in periods is over. Now we are going to talk about groups. Then what will tell? Increases and decreases, correct? No, in period. In groups it remains f block, it is below the periodical table, remains constant, it never not changes, fixed, constant, remains same or constant. Okay, example group 1. In group 1 we call that alkyl metals. ns1, its electronic configuration, it having 1 valency, it is fixed. No, if you take a group 16, that is group 16 group, it is co-halogens, its valency is 2 valency. valency replaced by the term oxidation. You see, valency is very very important. Now valency is replaced by replacing by the term oxidation state or oxidation number. Oxidation state or oxidation number. Valency just a number, does not have charges. Valency, first of all, it is a number, does not have any charges. You see, we will told that 2 valencies and 3 valencies and 4 valencies. We are told that, you see, 1 valency, 2, 3, 4. I am not giving any charges to this. Well, come to oxidation state, it has charge possessed by an atom. Okay, possessed by an atom. One thing, first of all, what we take that in valency just a number. Valency just a number, but don't have charges. When come to oxidation state, it has a charge possessed by an atom. Example, we'll take one example. While taking example, you can understand that. Example, that is, first we'll take that OF2. We see, if you take for oxygen, atomic number is 8, 1s2, 2s2, 2p4. When come to fluorine, 9, 1s2, 2s2, 2p5. Here, when fluorine, it has the valency is 7. It has 7. Okay. You see, while writing the diagram, this is the diagram for OF2. You see what happening here. Oxygen giving the electrons towards the fluorine, means one electron is giving, correct? No, it giving means it must be a +1. First I am talking about here +1, here -1, correct? No, -1. Now again we are talking here, again this one electron giving to this fluorine, right side fluorine, it again +1, here -1. Then what we can write, 0 F, correct? No, -1 here +1 becomes +2. The two electrons giving from oxygen to fluorine for left and right side. You are understanding here? Okay. Next we are going to talk about another example, that is Na2O. The sodium electronic configuration. First we want to write the sodium electronic configuration: 1s2, 2s2, 2p6, 3s1. The valency is only one valency. Okay, one valency. Then when we want to write the oxygen. No, oxygen already written in above: 1s2, 2s2, 2p4. You see what happening here. The oxygen gaining the electron from the metal, that is, 2 electrons are gaining, 2 electrons, because the P, it must be filled with 6, correct? No, the 2 electrons are gaining from the sodium, it becomes -2. Gaining, no, gaining the electrons, 2 electrons are gaining, then it becomes, what happens, 1s2, 2s2, 2p6, correct, no, 2 electrons coming. What happened here, 1s2 in sodium, 1s2, 2s2, 2p5, okay. Then the 2 electrons are leaving, then it is +2. You see, order of electronegativity for this element and also this element, order of electronegativity is fluorine is greater than oxygen is greater than sodium. You see, here what happened, the sodium is pulling the electrons from the oxygen, from sodium to oxygen. What I told you here, the oxygen giving the electrons to the fluorine, means you see the sodium giving electrons towards the oxygen giving electrons towards the fluorine. For that, we will write that electronegativity in order for FO sodium. It's complete the classification of periodic table and its properties. Okay.